Okay, so let's see what we're going to do today. So yesterday we looked at the formal definition of Kleene algebra and then at cat. One thing we haven't done, and I want to do today because this will be important later on, is to talk about what is the semantics of cat. And I'm going to also look at some examples of program equivalence. In fact, I'm going to go back to the example that I showed you the very, very first lecture of two while loops and how to prove them equivalent. And then from here, I'm going to start telling you about this special cat called the net cat. And hopefully today we do syntax and examples. And then we see how far we get. Okay, so for Kleene algebra, we did two types of semantics. We did the denotational semantics with regular languages, and we did the operational semantics with deterministic automata. So what I want to do for cat is pretty much the same thing. I want to show you what the denotational semantics is, and then I want to briefly show you what the automaton looks like. And the reason I keep showing sort of always the notational and automata is that the denotational semantics is useful because it sort of gives you the gist of what the program is doing, and it gives you a full description. And the automaton is very, very useful for implementation. So when you have both the denotational semantics and then a full correspondence to an automaton model, you can sort of pick and choose the best of both worlds. And when you're sort of reasoning about, say, program refinement, you might want to use the denotational semantics. But at some point, if you really want to implement procedures for equivalence, most likely you want to move to the automaton. Okay? So if you want the machine to do the work, the automaton is better. Okay, so what is the difference now? So let's look at the syntax of cat and what the difference is with regular expressions. Many things are the same. So I have 0, 1, I have some letters with some alphabet, I have plus, I have special composition and star. But now I have some tests from a Boolean algebra. And those tests, I can also describe them syntactically. I can say it's either a test, a basic test, or it is true or false, 0 or 1, or it is or it is and, or it is negation. Okay, and now here I'm going to be, I wrote in the syntax the distinction between the plus for tests and the plus for expressions, but ultimately I'm always going to use the same system. Okay, I just wrote the differences so that you remember these. And if you think about the definition of yesterday, what I've done here is really split my alphabet into two parts. Let's actually call this maybe A, which is P, the program actions. And basically what I'm doing compared to regular expressions.
You want to arbitrarily miss?
Let me finish my sentence and then maybe it will be clear. So what I've done in the syntax is saying I had an alphabet A in my Kleene algebra, and I've now split this alphabet into two parts, T and P. And I use P to generate the programs and T to generate the Boolean algebra. So these these are basic tests. Okay, these are the primitive tests. Does that answer your question?
No, I'm thinking about the other operands.
So yeah. This should be deep. Sorry, I thought you were on here. Thank you. And this, so this is the Boolean part. And this is the program. Okay. And the Boolean part is embedded in the program. So the way to think about this B, when I put a B as a program, I'm really thinking of it as an assert B. Okay, so as a test, when I embed it into a program, is an assert. Okay.
It's a chance you can push it a little higher.
The mic or the
Yes, the mic. Yeah.
Okay. So let's think a little bit about let's think about the semantics of Booleans, of the tests. And then we'll think about the semantics. So if I give you some basic tests, what is the semantics of this? Like if you're looking at the program that only has asserts, what do I learn in this? Someone actually answered the only thing I learned, if I write down a program that only has asserts, the only thing I guess.
Oh, is it after the assertion?
Exactly. So the assertion tells me something about the state of my variables, right? So if I write down some combination of asserts, and if I stare at it and look at the Boolean combination that an assert gives me, I learn something about the state of my variables. So let's imagine I have n variables, and they will correspond basically to, so my variables are Boolean. Okay, so that means I have n Boolean, I have n basic tests. And remember that every basic test has a brother. That's the component. Okay. So I have these basic tests and their brothers. And now, if I write down a sequence so if I write a list or a sequence of basic tests that can either be positive or negative, and I have to have exactly one per variable. What I have here is what sometimes is called a full test or a valuation. Because it actually tells me exactly for each Boolean variable whether it's true or false. Okay. So these are formally the atoms of the Boolean algebra generated by T. And atoms are sort of the minimal elements of a Boolean algebra. When you build a Boolean algebra, you have false. And then from false, you can add more information. Like you learn that P1 is true, P2 is true. And at the bottom, next to false, are these elements that actually tell you everything about every single variable. So let's imagine I have just two basic tests. Okay, T1 and T2. And I have their values. Okay. If I'm generating tests just from T1 and T2 by generating Boolean formulas, what can I get? Like, what information can I have? Maybe maybe both variables are true. Or maybe the first one is true and the second one is false. Or maybe the first one is false and the second is true. Or maybe both are false. These four atoms describe completely the state of any possible state of my variables. So at any moment in any program that manipulates variables x1 and x2, if I tell you at that moment which alpha holds, you know exactly what my variables have. Which means that if in the next step of execution I have a conditional, you know exactly which branch of the conditional is going to be taken. Okay, so these atoms, maybe by now you see this, they are nothing else than subsets of tests. Because if I give you a subset of tests, you can just say, okay, those are the ones that are true. Anything that's not in the set is false. Okay. So if I give you two tests, how many subsets do I have? 4. It's either the empty, the one with Q1, the one with Q2, or the one with both, right? So empty, the one with Q2, the one with Q1, or both. Okay. And look at the type of this. I wrote the subset as a function, as a characteristic function, because look at its type. It's from T to 2. And my variables are Boolean. So it's just telling me, for every variable, is it true or not? Okay, so now we know that the semantics of anything in here will be a set of atoms. Okay? So the semantics of a Boolean is a set of atoms. So it's a set of sets of this. Why? Because every basic test induces a set of atoms. Because the only thing that every basic test tells me is like what happens in one place. And all the rest is up for grabs. So I have to get a set of atoms. And then for every element, I take intersection, I take union, the empty set, and the set of all the atoms. Okay? And now we're going to use these atoms to talk about the semantics of programs. So remember, for regular expressions, every regular expression is associated with a set of traces. Okay? Now the notion of trace for cat, because we have these tests, is a little more complex or a little more structured. Because I want to be able to say, every time I take a step, that step might change the state of my variables. Okay, so a trace for cat programs is going to look like this. This big enough. So here's what a trace looks like now. Every time I take an action is, some program. Every time I take that action might change the state of my variables. And so when I'm running my program, I start with something in my variables. I take an action, something else might be in my variable. I then take another action, something else might be, and you go on until you take the last action, and that last action might still change the state of my variables. So I end up with an atom at the end. So the strings before, they were elements of A star. Now we have elements of at, P, star, and then an atom at the end. Okay, so I have these interleaved sequences of atoms and actions. And then at the very end, I have my last state. Yes, sir. What's an action? An action is just so I sort of took a subset of my alphabet and I said, these are program actions. So CAT is about uninterpreted programs. So the letters of the alphabet can be standing in for things like X becomes 1, but I call it P. I don't tell you the P. So P, one of these P's might be standing for something like X becomes 1. Okay. So then the semantics of this P somewhere is going to really tell me that my alpha, if I have an alpha, then the next alpha has to be such that X is now 2. But I don't actually tell you which X is touching. I just tell you how P changes the state. Okay. All right. So where were we? Yes. So the strings are now elements of, so I have alternating sequences of atoms and actions, and then an atom at the end. Okay, yes.
The string of state action looks a lot like for logic. Are we able to port any of our knowledge?
Yes,
there?
I will say that in 5 minutes. Maybe.
Oh, okay.
Is there a line-based standard that
So all I'm talking about are uninterpreted expressions. So I'm not touching any. Like if I unpack what my P is, then suddenly I might have to worry about some more stuff. But right now, P is just an 8. Okay, so I'm not going to touch the variables.
thinking about something like X, Y.
Yeah.
But you don't know
So I'm not allowing you to do that. I just removed that, and then I don't need to. Any more questions? I feel laughing. You're like, oh yeah, you just remove the hard stuff, and then it's easy.
Yes, we have a big program.
Yes.
For 0, I think we get P0 as the whole program.
So in the netcat example, I'm going to give in a little bit. We actually have done that. We've talked about input-output behavior, where we just pack the whole network as one key, and then you just want to know what the alpha at the beginning and the end is. That's a possibility. Like you have the option of refining where you pack the P. Yeah.
Your demonstration yesterday of the matrix thing has me thinking about, is it helpful in any way to represent these sets of truth values for your T's as like a matrix where you can go to different states based on the different transitions of the program, or maybe as a graph or something? I don't know what that gets you.
So like with CAT, there's a matrix representation of these things, and you can compute all the operations on the matrix. And in fact, when you reason about equivalence, you can use matrix operations. Even cooler, I think. Other models too. You can represent these Boolean expressions as BBBs, which are binary decision diagrams. And beautifully, you can represent this as something called, so many things, but I'm going to call it FDDs, forwarded decision diagrams, or BDDs with values. Maybe that's a better name. There's a beautiful paper, I think it's called 15 by Damian Luz, where he looks at symbolic ways to reason about equivalence of these programs. He formalized all of this in code, and he basically encodes all the expressions as some form of binary decision diagram, and then shows how equivalence is very, very easy. So there's a lot of again, because it's an algebraic view on program equivalence, you have a lot of structure that you can then explore for data structures. So this is a very nice paper, and as a formalization, who are interested in that. Okay. Let me see where I am in my notes. Right, let me write down all this, the actual semantics for programs. So I want to write the function like before, that for every program gives me a set of strings, but now the strings are these things, and these are actually called guarded strings. Because they are guarded by the atoms. Okay, so if I have any Boolean, and that includes 0 and 1, what I end up assigning here is a set of atoms such that the atom implies this Boolean. Okay, so this here, you can probably see how to define this. This is just saying alpha is a valuation that tells me for every t whether it's 0 or 1. So I can just instantiate that valuation to be, and it has to be true. Okay, so for instance, T1, T2 implies T1 and implies T2, but it definitely does not imply T2. Okay, so just telling you what things I can deduce. It also implies T1 or T2. It also implies T2 and T1 and things like this. Okay, so for every Boolean formula, I can basically define, this is the notion of satisfiability that you see. Okay. Now, if I have a program action and I have no information about what that program is doing, then the semantics has to basically tell me that that program action can potentially transform any state into any state. Okay. Now, this is a denotational semantics. There is also a relational semantics of CAP in which I give you for every P a relation on atoms, meaning I tell you what P actually transforms an atom to another atom, it's called this RP. And then in that case, you can write a finer semantics. So if you know a priori what every action does to every atom, then you can write a finer semantics. But at this point, in which I have P completely uninterpreted, I do not tell you what P does. The only thing you know is that P can transform any alpha into any beta. Okay? Okay, then for plus, it's still just union. And now comes the interesting case. Interesting case is always sequential composition. What do I do with sequential composition? So for regular expressions, we just concatenated E, like we just took a string from E and we concatenated with F. Now, what's the problem now? Why can't I just concatenate the two strings? Yeah, the type doesn't match because one string ends with a guard, the other one starts with a guard. So if I just concatenate them, I have two guards, and suddenly the type is wrong. So what I need to do, I wrote this as a diamond. Instead of, so for every string, alpha P that ends with alpha K, and then I have another string here that starts with a beta and goes on. When I'm concatenating them, I need to match the beginning and ending atom. So because this string tells me program E executes starting from state alpha 0 and ends in state alpha K. So if I now want to continue with program F, the only way I can continue is that if F allows me to start with state alpha K. If for some reason F does not allow me that, then I'm done. Okay, so this new concatenation operation basically just takes care of checking that the atoms are the same and just takes that pattern. That's the concatenation, okay? So the concatenation of these would be alpha 0, P 0, alpha K, and then let's call this Q0 here. Q0 and Q. So it deletes the repeated after because it's the same. Okay. And then star is just defined as before, but now concatenation is this diamond. Okay. Okay, let's do one example of this semantics to convince ourselves that this makes some sense. And then let's prove those two programs from before the same, and I'll give you half of the solution of the homework, which I hope none of you has done because you have an evening lecture this week. So if any of you did the homework, I'm going to be very impressed. Okay. So let's do an example. Yes.
Sir, I might have dismissed this, but could you repeat what procedure you use for reconciling two atoms?
Yeah. So if I have an atom, alpha and beta, and this atom is the end of some string and it's the beginning of another string, then there are two cases. Either alpha is beta or alpha is not beta. If alpha is not beta, this is just not defined. So I say that this operation is undefined. Because if alpha is not beta, if this is a computation and this is the continuation of that computation, I need to avoid. Because it's telling me this computation requires you to end in, say, P1 is true and P2 is false. But this computation can only happen if P1 is false and P2 is false. So think of this as a Howard triple, if you like, or a precondition and a postcondition. The postcondition of this program is that I end in T1 true and T2 false. The precondition of this program is that I must have T1 false and T2 false.
So it's a Howard triple, but where the pre and post conditions are restricted in what they can be, because what I was confused about is if they were Howard triples, then sometimes you could say like the post condition of the preceding statement implies the precondition.
Right, but because these are atoms, these are like fully determined. So either they're the same or they're not the same.
Okay.
There's no implication. So if I write alpha implies beta, this is only true if alpha is beta, because they are fully determined. On the other hand, if I write alpha implies B for some arbitrary B, this can be true for many B's, because now this B could be something like alpha or beta, or beta prime. Okay, but in the case in which I have exactly alpha and beta, there is no way that one implies the other unless they're the same. Okay? All right, what is the semantics of if then else? Cheng, are we okay?
Yeah, there's some audio issue trying to resolve that. It's okay.
Is it my?
Yeah.
Okay.
Okay.
If B, then P, else Q. What is the semantics of this? So remember from yesterday that we are defining these as B, P plus not B, Q. So it's just a syntactic sugar for that. So what is the semantics of this? Well, it is the semantics of BP union the semantics of not BQ. And what is the semantics of BP? That's the semantics of B, diamond, the semantics of P. Okay? union, and I'm going to leave this for a second there. What is the semantics of B? The semantics of B are all atoms that imply B. And I'm trying to concatenate that with a set that says I can do anything around P. Okay? So now what does this diamond do? This diamond tells me that whenever I'm taking the first branch of my if then else, I better be in a state in which B is true. Right? So what I get here, when I concatenate, I get alpha P beta, in which alpha has to imply B. So this concatenation basically restricts now this alpha here. It tells me that that alpha must imply B. Okay? And I union these then, you can imagine how that goes, with all alpha cube beta such that alpha implies not B. Okay? So what my semantics is saying the semantics of if then else has two types of traces. It has one type of trace in which I start from a state in which B, the guard of the conditional, is true. And in that case, you take the then branch and execute P. Or you started from a state in which the conditional, the test is false, and therefore you must have taken the else branch and executed Q. Okay? So this is somewhat sensible, I would argue. Yes?
Sorry, I might have known, but I just wanted to clarify the difference between the hollow diamond and the full diamond, if that is significant.
The what?
The hollow and the full diamond.
Oh, no, this is just me being, sorry. Sometimes while I'm thinking, I color stuff. And yeah, sorry. This is the same symbol. Sorry. I was just probably thinking what I was going to say next, and so I color. Sorry about that. It's the same symbol. Okay. And if you look at, now these I'm just going to show you. I'm not going to do the calculation. If you look at the while loop, which was, you might remember from yesterday, BP star not B, what you get in the semantics of these, you're going to get things like alpha that implies not B. You're going to get, actually, let's call this beta. Alpha P beta, in which alpha implies B, and the beta always implies not B. Then you're going to get alpha P beta, alpha P beta, and so on, in which the alpha implies beta and alpha implies B and beta implies not B. So every trace is longer and longer, but every intermediate state has to imply B for the loop to execute, and at the end, beta has to be true for the loop to exit.
In the bottom of this if then else case, what is beta?
Anything.
Anything?
Yeah, beta is anything. I haven't restricted it. Yeah.
Do we really require the same alpha?
No, I'm just being sloppy.
Yeah, I was wondering.
Yeah, I just didn't want to write alpha 0. Yeah, I mean, okay. Alpha 0, alpha 1, alpha 2, and then the condition is all the alpha i's implies B, and the beta implies not B. Yeah. Max.
What happens if our traces are infinite? It looks like there's if I understand the notation of the bottom left, it looks like the traces seem to be finite.
Yeah, the traces are finite.
Okay.
So yeah.
What about programs that don't terminate?
in a very, very funny way. No. I mean, in a way that people would argue is not right. And I will argue that for some definition of right, it's okay. So what happens to, yes, I will repeat the question. 1 second. So the question was, the semantics seems to only have finite traces. What happens when the program doesn't terminate? That's the question. So Max is worried about something like this. So what happens is that if you work out the semantics, you're going to say that this thing here is the same as 0. Okay, so what's the rationale for this? And I mean, let me be clear. This is very debatable, and there's alternative semantics in which you actually record the infinite traces. It's just that the moment you start recording infinite traces, you enter, when it comes to equivalence, you enter a space you might not want to be in. So what this is saying, and this is something that occurs in a lot of algebraic literature, this is saying, look, with non-termination, your observation power is none. Because you never exit. So if I concatenate this with some other program, I never actually get to execute the other program. So even if this program that comes next has some observable behavior, I haven't seen it. And because cat is uninterpreted, even if I write P here, I can't really see the effect of P, because I never actually got to check what the effect of P is in my next program. And therefore, non-terminating programs are sort of mapped to abort. And again, this is debatable, and we could debate why this is wrong. But for some verification tasks, this is a perfectly okay.
Could you argue because the in the system to B is true, because we are concatenated in a while loop with not B at the very end, the entire thing becomes 0?
I mean, that's how you prove that these two, that's exactly how you prove that these two things are equivalent. Yeah. Okay, other objections?
Well, I was just wondering, does this imply that all non-terminating programs are equivalent to each other then?
Yes.
Okay.
Which again, we can debate. But I mean, in a language with no effects, this is sort of okay. The moment you add effects, this is a little bit problematic, right? Because, sorry, the question was, thank you. The question was, oh, I forgot what the question was. I know what the answer
all
is.
Non-terminating
yes.
program, yeah.
Are all non-terminating programs the same? And the answer in this setting, yes, they are all the same.
Yeah, I think originally, if we want to work on a program with whole triples, and if the program is not terminated, the whole triple doesn't hold. So in original, I think we can't work like that because our program maintains all triples. I think that's not the fault of algebra. It's just the nature of this kind of program.
Yeah, so the question was, isn't this sort of similar to what happens with Hort triples? And in some sense it is, because a lot of the semantics for Hort triples is defined with partial correctness, which means that you assume the program terminates in order to actually make the statement. So yes. And this is a good point for me to say, how does this connect to Hort triples, which is a question someone asked a while ago. So if I have a Hort triple that looks like this, some program C, and then some. So B and C are tests, so they are some element of my Boolean algebra, and C is a program in my simple imperative language. And basically, the validity of this Hort triple that says under precondition B, if I execute C and it terminates, then at the end, the postcondition C is true. So this will be the same thing. So the validity of these is the same thing as, let me see which one I want to show. Let me make sure I don't write anything wrong. there are three different characterizations of this, but the one I like is this one. B, C, not C is 0, which says if I start with B and I execute my program C, and now I try to filter out all n states that would render the post condition false, this has to be empty. Meaning that in fact, every single trace I got from BC is the same, is non-empty. Okay, so this is kind of perhaps a funny way of expressing the validity of a Hort triple, but it gives you a sort of cat equation to check. And then there are others. There's one that Dexter likes that goes like this. It says everything I can obtain from doing program C under precondition B is contained in executing C without knowing anything and ending in little c. Okay. So these are equivalent. Kind of a fun thing to show that these are equivalent. So this means that, the reasoning power that you get in CAT subsumes propositional for logic. Okay? I feel I'm not going fast enough. Let me see what time it is. Okay, good. So let's look at one example. Let's look at, okay, let's see. I want to show you half of the solution of the homework, and then I want to look at that program that we saw in the first day and see how we would prove it equivalent. Okay? So let's do the reason I want to show you part of the solution of the homework is that it's used in the equivalence of the program. Okay, so one of the exercises in the homework, the one I said was the hardest, was the denesting rule. And the denesting rule says that if I have a program that has an if then else, then this is the same thing as this program with lots of while loops in them. I get all the stars right, yes. Okay, so let's prove that. So the way to prove this, that these things are the same, you need to prove it in 2 steps. So you need to do 2 inequations. I'm going to do the one from left to right. So I'm actually just going to prove half of that and show you that. Okay, so how am I going to prove this? I'm going to use the fixed point rule. And in order to use the fixed point rule, I'm going to observe a couple of things. Namely, I need 3 things. Okay, so first fact. 1 is smaller or equal than x star y star x star. Okay, who tells me why I can write that syntactically?
1 plus anything is anything. Or, no, sorry, that's not true. 1 plus anything squared.
Yeah.
Yeah, I was going to say 1 plus anything star is anything star.
Yeah, that, correct. So 1 is smaller or equal than any star, any, say, z star. Okay? So in particular, 1 is smaller or equal than x star, and 1 is smaller or equal than x star y star. And now I can put this together by saying, well, then 1 concatenated with 1 is smaller or equal than this thing concatenated with x star. And then 1 concatenated with 1 is 1. Okay, so there's a lot of steps, but ultimately it's basically just telling me that 1 is below any star. Okay, so this is a fact. Second fact that I need is that x star, y x star star is smaller or equal than x star, oops, y x star star. Let me see if I got this correct. Okay, this is again sort of easy if you ignore. So this is the same term, so ignore it for a second. And now I'm just really using the fact that x star is smaller or equal than x star. Okay, and how do I prove that? I unfold the star once. This gives me 1 plus x star. And then at that point, I can see that, you know, if I sum this term with this term disappears. Okay? So here, this is what I'm using. I'm just using the fact that this term here is smaller or equal than this term here, and then I'm appending something that's going to be convenient later. Okay, then the last thing I need is that y, is that correct? Yes. Yx star, yx star star is smaller or equal than yx star star, and that is smaller or equal than x star x star y x star star. See again if I got that correct. Yx star x star yx star. Okay. Let's look at the first part. The first part is just an instance of what I said here, where x is this complex thing. Okay, because this term is the body of the star here. Okay, so this is one. How about this one? This one is a little bit funny. What am I using here to go from here to here? Who sees that? Yes?
I had a question, actually.
Oh, sure, go.
I'm a little bit confused about the notion of less than or equal to in this context, because thinking about it from a regular expression perspective, you know, x star can produces fewer strings than just x star, but
Sorry, so let me just write the definition and then I'll repeat the question. Okay, so first part of the question, what's the definition? This is the definition. E is smaller or equal than f if I can prove that E plus f is f, okay? And now the second part of the question?
I think it was just confusing because when you think about a regular expression and the languages that they can represent,
Yeah.
You think of x star as representing a smaller language than just x star because it excludes the empty string. And
That's correct.
That's why I got confused.
That's correct, and that's the right intuition, because x star is indeed smaller as a language than x star. So if I look at the language, it's contained in x star, right? Because it's smaller. So the intuition of the smaller equal is precisely that. So you're totally on point.
Thank you.
Okay, so just what am I using here to go from here to here? Can anyone see? Yes.
You're using that there's like an empty case for x star, and that when you expand out the x star on the right side, you make it 1 plus x.
Yeah, so I'm just using that 1 is smaller or equal than x star. And I sort of can put a 1 here and just add x star. Okay? Okay, so is everyone happy with these 3 facts? So these are facts. And you would have, I mean, you know, I'm giving you the proof already done. So it's kind of coming up with these facts would imply doing the proof sort of, I'm doing the proof now bottom up, but really these proofs are done top down. You start expanding the star, and then you find what you need, and then you prove those. And I'm giving you the proof already the other way around. So what I'm going to do with these 3 facts, I'm going to combine them and say that, so sorry, if I look at this, if I look at the left side, these things here, so look just at the left side for a second. I can write, if I take the sum of all things on the left side, I can write these as 1 plus x plus y, x star, y, x star, star. Does everyone see that? I just took the sum of these 3 things on the left. Okay? And on the right, I am almost good, except I don't have exactly the same thing. But if you do the other part of the homework, then you can use the sliding rule that says that this is the same as that. And now I have the same thing, so that's cool. I can just write x star y, x star star. Okay. Now I'm in great shape because I have, not in great shape there. I have that, and I have that. I'm going to call this curly x. So what I have here is 1 plus something times x, smaller or equal than the same x. So at this point, I can apply my fixed point rule and conclude that x plus y star concatenated with 1, but I can sort of forget about that, because concatenating with 1 does nothing, is smaller or equal than my x, which is x star y, x star star. So here I use the fixed point rule. And if I did this correct, hopefully, I'm done. Okay? Yes?
So the way you probably, or if you were to solve this proof top down, the way you would probably do that is to try to apply the sliding lever to x star, y star, x star.
Yeah.
Distribute, prove each part individually.
Yes. I mean, if you try to do it like you would do it, really, you will encounter at some point, I mean, you sort of slide here, and then you start unfolding here, because it's the only thing you can do.
Yeah.
And as you unfold, you encounter the 1 plus x plus y something. Okay? So just a couple of remarks, right? I mean, I showed you this proof. I knew how it goes. It sort of looks okay. Whenever you try to do these proofs yourselves, it's much harder, because you need to get it. First of all, you need to get a lot of practice in them. But second of all, there's no deterministic way of applying these steps. At every step, you might have different candidates. So reasoning with the axioms is nice in many ways, and gives you a highlight of the structure, but it's also hard in many other ways. And that is why sort of automata-based procedures to talk about equivalence are the norm for implementations. Even though, like in terms of complexity, deciding things with axioms is the same complexity as deciding with automata, ultimately, in terms of mechanizing the procedure, is much easier to mechanize the automata procedure. Because the automata procedure has this flavor of derivatives. You take a step, you check something. You take another step, you check something. And it's a very sort of, you don't need to think. You just keep applying derivatives. And because there's a finite automaton, you know that the worst that can happen is that you need to go through all the states, and that's it, okay? But the algebraic reasoning sort of gives you more insights into the structure, and this appears then later in extensions of Kleene algebra with tests. Okay, before I move on to tell you how you would do the proof of the programs, I want to make a few remarks of things I won't be able to show you in this spirit of what is there for cat, okay? So cat has, again, a soundness and completeness result that tells you that the axioms of Kleene algebra, the axioms of Kleene algebra plus Boolean algebra are all you need to decide whether two programs are the same. There's an automaton model and this automaton model is deterministic, but the transitions are pairs of atom action. And instead of having a final state, you have a final set of atoms that tells you what tests can you actually validate at the end of your program. So this is called a cat automaton. And this whole automaton can be very efficiently represented as a BDD. And that's in Damien's paper, in some other papers. The decision, so the equivalence of these automata is decidable. And there are several decision procedures. One using BDDs, that's very nice. But there's others using matrices. This is due to Cozen. And this is due to Hoos. And these procedures are in p-space. So just like for deterministic automata. However, and I want to mention this work as well, even though this equivalence is in p-space, the way it actually works for a lot of programs is very efficient. And one thing I mentioned to some of you yesterday is that some of these procedures, like the way they are implemented, especially the ones that don't use BDDs, make use of the union find data structure that goes back to Hopcroft, Tarjan, and others. So the union find data structure was, was sort of designed to reason about equivalence of automata. And so you can use it to encode the relation that tells you how two automata are the same. And this gives you that the equivalence, if you're checking the equivalence of two non-deterministic or deterministic automata, you get something that is in O n log n, in which the log is defined over, let's write here C, is defined over the inverse of the Ackermann function. This is really not super relevant. The only thing that's relevant is that this log is very, very small. This becomes a very, very small constant almost. So in the original paper that Hopcroft and collaborators wrote, they actually conjectured that the equivalence was linear because they didn't realize that there was like an extra thing here. And this is what Tarjan corrected a few years later and said, yes, it kind of looks linear, but it's not really. There's like a small factor there that you missed. Okay, what is kind of incredible about this was done in the 70s, 80s, is that there's actually a way of improving on this. And so there's a paper that talks about a very general technique called co-induction up to. And they instantiate these for non-deterministic automata, deterministic automata, and I'm going to write these as Brozovsky derivatives, which is automata in which the states are regular expressions. And they actually show that using co-induction up to, you can't improve the theoretical limit. I mean, the theoretical limit is a theoretical limit, full stop. But the number of checks you need to do gets incredibly small. And so you can much more efficiently, in practice, if you look at benchmarks, you can much more efficiently check equivalence of any of these things. And what they are using here, the up to, refers to the fact that when you're building your union-find data structure, you're sort of connecting, so you're connecting states. Maybe you have an automaton like this, and you're connecting your states. And maybe the way you're connecting your states ends up doing something like this. Let me see how I do this. And then this goes back here. And this goes back here. And then you end up something like this. And I forgot how you do this, but you basically can find yourself in this worst case scenario in which you've connected every pair. But the reality is, even though you connected every pair, you didn't have to, because inside your proof, inside of your union-find data structure, there's this chain of connections that tells you that if there was any problem with your equivalence, you would have found it much earlier. So you can stop the check of your equivalence much earlier if you notice that you already have a check of things. So namely, when I'm checking something between these two states, I don't need to check it because there was a sequence of connections that tells me these two states are fine. And so they came up with a way of stopping the procedure from Hopcroft and Karp much earlier by taking into account the structure of your relation. So that's one technique. But if then you have expressions on your states, you can do even more. Because if at some point you see E plus F, and then here you see F plus E, again, you don't need to check this. You know they are the same. You know you've seen E plus F with a bunch of things. So you don't have to continue. And so they kind of developed a series of techniques that when you're doing the check that was designed in the 80s, you are just allowed to stop earlier. And you show that it's a sound technique. You show that stopping earlier does not like miss anything further on. And by doing that, you just get a much quicker way of checking. Okay? In the worst case scenario, you might still not be able to stop earlier. You might be unlucky that you never have such a pattern. But in many practical sort of tasks, you actually can stop much earlier. Okay, so I want to mention this paper. And this is a paper. It's Bonke and who's Popple 14. So it's 10 years old now. Okay. So let me see if I forgot to mention something. No, that's pretty much it. So these are things I don't have time to mention to show details, but if you're interested in this stuff, these are sort of cool to go and look at them. Okay, we have 10 minutes, and what I'm going to do, we have 10 minutes, is that correct? Yeah. 10:20 is the, okay. What I'm going to do in my remaining 10 minutes is get started on netcat and just tell you pretty much the syntax, and then tomorrow we do the semantics and the example. Oh, yes, and I forgot to say, sorry. No, I cannot do netcat yet because I promised you I would tell you how to prove the example from the first lecture. So the example from the first lecture was while B do P followed by while C do Q. It's right here. So we wanted to show that that's equivalent to something else. What is this as an expression? This will be BP and then CQ star not C star not B. Hopefully I didn't make a mistake in that. Okay, so this is expression number 1 corresponding to that program. And then the other program was if B, then P followed by, I'm really confused by my own notes, while B or C do if C if C then Q else P. Okay. And there's no else branch here. So this whole thing is inside the if. And so the question is this equivalent to B followed by P followed by B plus C, CQ plus not CP star, not B, not C, and plus not B. I believe that is correct as well. Okay, and now how do you prove that these two things are the same? You have this, and here you have that. And what you're going to end up with, you're going to end up having to distribute all these pluses over. And once you have everything here written as a sum, what can you apply? Because you have a sum inside a star. Oh, I deleted it. You can apply denesting. And basically that's all. Together with some simplifications afterwards. Basically what you do to go from this program, to the simpler program, you do some distributivity here. You end up with some simplifications, like if you distribute C over this else branch, you end up with C and not C, which kills that branch. And then you end up just with 3 sort of things. And then you do denesting on those. And then once you have denesting, I'm looking at the proof in my screen. Once you have denesting, you have to just apply sliding. Once you denest, you apply sliding to capture this BP here. And that's how you end up with BP on this side. You could also work to then apply sliding on this side. But basically, that's what to do this proof, the 2 steps that are sort of tricky, apply denesting and slide. Okay? And I will share a screenshot of this proof if you are unable to do it. But basically, once you have denesting and slide, this proof is not so hard. Okay? So I just wanted to mention that. And now I only have 8 minutes. So let's see if this is enough to at least introduce you to netcat. Okay, so let me tell you a little bit about netcat. Netcat is a cat. And when I do this with slides, I have cats in my slides, which is... we actually have an official cat for netcat called Carbon. So if you go to the ACM, page on the POPL 15 and the POPL 16 papers on netcat, the official image of our paper is Carbon. And Carbon is a sweet cat that's living with me right now, but he's Nate's cat. He's Nate Foster's cat. So this is the Foster cat who's living at my house at the moment, because Nate is on sabbatical. But yeah, so if you want to see something fun, I'll tell you something else. There is an Easter egg inside both papers. If you zoom in about 400% on the sequential composition, inside there, there's Carbon's eyes. If you can find that, you'll, it's a little bit creepy, but, and the paper takes about 10 minutes to compile. But apart from that, what you do is what you do at like 4 a.m. the day of the deadline. No reviewer actually realized, but so anyway, so comments on cats aside, netcat is a special cat. So what's the idea? Like, how did netcat come about? There was this language that Nate had been working on called netcore. And they wanted to develop a language that would enable you to reason about network reachability. For the purposes of what I'm going to show, and in general, for the netcat papers, we think of networks as, let me write this as square so that you don't think this is an automaton. Think of networks as a bunch of boxes, which are switches, and the only thing these boxes can do are they get packets in, they get little packets. You know, the packets go in, and these boxes are allowed to change something about the packet. So they might, you know, this packet might say, my destination is 1, and then it gets here through some box, and the box actually says, actually, let's send you to destination 2 now, because that's what I want. And the packet goes on and sort of moves through the network. So for the purposes of, you know, of what I want to show you, we think of packets like there's a set of fields, and this set is finite, so it can be, you know, it has fields like F1, F2, and so on. And there's a set of values that I can put in those fields. And for the purpose of what I'm going to show you, I also assume that these values are finite. And so what are packets? Packets are just records that tell me for every field, what value do you have stored in that field? Okay, so think of packets as just, you know, packets are like a sequence of things where you have your fields here on top, F1 to Fk, and for every field, I have some value in there, V3 or V4, you know. And I'm assuming that all values are set. Like in the beginning, I write zeros everywhere, so it's kind of, I don't have undefineds anywhere. Okay, so this is my sort of new first-class citizen. I have this record of fields to values. And now I want to talk about what a network might do to these things. And, you know, I want to be able to capture the fact that the packets might come in into some node, and the fields of this packet get changed. Or maybe one of these nodes is some sort of firewall, and it says, if a packet comes in of type SSH, do this. If the type of the packet is something else, drop it. Right? So I want to capture the fact that these nodes are able to test the values in my packet. And you're starting to see maybe where I'm going. So the thing I can do, I can test values, and I can set values. So netcat is a cat where the tests and the actions, so this is my P and this is my T from before, the program actions and the tests are pairs. So they are interpreted. They are interpreted in this world in which I have one packet. Okay, I have one packet for now. And this one packet can be transformed by changing the value of a field or by testing the value of a field. So let me show you your very first netcat program before we need to stop. Let's imagine that in my fields, I have things like, I have the following fields. I have SW that tells me which switch I'm at. I have type, which can be things like SSH and other things. And I have port, the port in the switch in which I might go in or out. Okay, and I also have destination. DST is just destination. Okay, here's your very first netcat program. Says if I am in switch 2, and the type of the packet is SSH, then I'm going to send the packets out on port 4, and I'm going to set the destination to, oops, the destination to 10 to some random thing. Okay? This is your very first example of a netcat program. And the intended meaning is that this is like a packet filter. So think of this as a huge box. And it tells me for any packet that comes in, it filters the packets using this test. The only packets that get through have to be in switch 2 and be of type SSH. If they pass this test, then I get to set things in those two fields. So the packets that go out will definitely have that they came out in port 4, and the destination is that number. Okay? So using this somewhat, simple interpretation of CAT, I want to show you tomorrow how you actually do network reachability. And I will leave you with a parting thought, which is because suddenly I'm interpreted, more equations are going to hold. Namely, what happens if in my program these are just 2, there are 8 of them. But what happens in my program if I say f becomes n followed by f becomes m? What should happen? Only the last one survives, right? If I test that my field is n, and then I set my field to n, it's only the test, because if it's already n, then what's the point? And the same thing, if I first set to n, and then I test, then the test is irrelevant. It is irrelevant in the sense that it's going to hold trivial. Okay? And there's 5 more that I will show you tomorrow. But basically, the special CAT has all the axioms of CAT, but then on top, because I now have these interpreted actions, I know more about what the actions do. And in order for the axiomatization to be complete, I need to integrate what the actions are doing. Okay? So I'll show you that tomorrow together with an example. So thanks for coming early in the morning, and I'm happy to take some questions.